Hello Lancers, today we're going to talk about forces and how they interact with our lives, and we're going to get through all the way through Newton's first law, so that's our plan for today. Let's begin by identifying what is a force. A force by definition is a push or a pull. So you can think about anything in your life that pushes or pulls, you could consider a force. Okay, so if you're talking about what is a force, if you take and push a wagon up a hill, you put a force on the wagon. If instead you get a tractor and the tractor pulls the wagon up a hill, the tractor is putting a force on the wagon. And so you can have all sorts of different forces. If you take a magnet and use it to push another magnet around, the magnet is putting a force on the other magnet. So anything that might push or pull on something is a force. We have a specific unit for force. It's named after Isaac Newton, and it is the Newton. But a Newton is not in itself an isolated unit. It's what we call a compound unit. So built into it are a bunch of smaller units. In this case, the kilogram meter per second squared. So a force is a kilogram meter per second squared. And we typically refer to that group of units as a Newton, and that is the measurement of a force in proper SI units. In non-SI units, we have another unit for force which you may be familiar with. It's called the pound. Wait a minute, I thought the pound was how much you weigh. It is, because it's a measure of how much the Earth's gravity is pulling you down, which is how much you weigh. And so a measure of the force of the Earth on your body is what we call weight, and that's in pounds. But in physics, we don't use the English system pounds, we're using the metric system, so we'll be using newtons. Okay? So we identify the different types of forces based on what causes the force. And we have many different things that can be. So one of the things we can identify is the force of gravity, which I was talking about. We symbolize force of gravity with a capital F followed by a little g. Capital F, lowercase g, force of gravity. Please don't ever change that. Force of gravity will always be a capital F followed by a lowercase g as a subscript. The F for force, a subscript g, let you know it's the force of gravity. This is the pull of the entire Earth on the object. Please understand that gravity is caused by the entire Earth being beneath you, so Earth is pulling you down. So what causes the force of gravity is to pull the entire Earth on the object. It is the exact same thing as weight. The only thing we say is slightly different is when we talk about how much you weigh, I don't go around saying I weigh negative 200 pounds. I say I weigh 200 pounds because that's the way people talk. However, technically, since we typically use down as a negative direction, force of gravity should be negative as well because force is a vector. And as a vector, we have to follow the proper protocols where one direction is positive, the other direction has to be negative. So if we're making up positive, down will be negative. That's typically what we do. The formula for force of gravity is the mass of the object. Now, mass and weight are different. Mass is the amount of matter in an object, and that's in the unit kilogram, whereas weight is the pull of gravity on that mass. So that is mass in kilograms, and g is the acceleration due to gravity, which is this to 9.8 meters per second squared, or negative 9.8 meters per second squared, giving you a negative force of gravity. Okay? Some other force categories. Force normal. Now, this is not a force that's different than weird. If you look up force, or the word normal, in a dictionary, what you will find is that there's two definitions. One is like the opposite of being weird, but definition number two means it's perpendicular. It's at a right angle. And so, we're using that kind of terminology here. This is the push from a surface perpendicular to the surface. So force normals, or forces from surfaces, always act perpendicular to the surface. Take, for instance, this tub that used to have cheese in it, and my hand. Now I'm interested in the forces on this tub. Well, obviously gravity, or the earth, is pulling down on this tub, but my hand is putting a force upward on the tub. That's the force normal from my hand to the tub. What direction does it act? It's acting perpendicular to my hand. We could create a new situation. You wait there. I'm going to grab a ramp. All right. In this situation, I have a ramp, and I don't have to hold it horizontal. I can hold it at an angle. When I'm holding it at an angle, the force normal is not directed straight up. It's directed perpendicular to the surface. It will be tilted. It would not be straight up. It will be tilted because it has to be perpendicular to the surface of the ramp. So your force normal is always perpendicular to the surface. That's important to know. Force of tension. That is any force that is being delivered through a rope, chain, string, etc. So anytime you're pulling on something through sort of a medium like a rope or chain or cable, you're going to call that a force of tension. So the next type of force is the force of friction, and by definition the force of friction is a force that will always oppose motion that is caused from two surfaces sliding together parallel to each other. So you remember force normal was when two surfaces were in contact, it was sort of pushing perpendicular to the surface. This happens when there's a force that opposes the motion of two surfaces sliding. So it is a force that always opposes the motion, I should have this, of two surfaces sliding horizontally. I'm just going to abbreviate that. So a force that always opposes the motion of two surfaces sliding horizontally. The formula is force of friction is less than or equal to mu times force normal. Less than or equal to? Yeah, because it's not necessarily equal to, because force of friction will always oppose motion. So let's think of a situation. Perhaps you have a tub on a container, and I'm pushing, trying to make this move with, let's say, 3 newtons of force. So I'm pushing that way with 3 newtons of force. Well, if I do that, force of friction, let's say it can oppose that with, if I calculate mu times force normal, let's say in this situation mu times force normal is 5 newtons of force. Well, since the force of friction is going to oppose that motion, and I'm pushing with 3 newtons this way, force of friction is going to oppose and push that way, but it's not going to push with this full 5 newtons. Force of friction could be 5 newtons. It will not push with 5 because that will cause it to slide this way. So it's only going to be as big as it needs to be. This is a maximum value. So if I'm only trying to make it move with 3 newtons, friction is only going to try to keep it stationary with 3 newtons, so that the two forces will be balanced. The net force will be 0, and it won't move. Now let's say I push with 4 newtons. Well, then the force of friction would increase its value to 4 newtons, and it still would not move. If I increase my force to 5 newtons, force of friction would also increase to 5 newtons, and it would not move. If I increase my force to 6 newtons, force of friction can't get any bigger. And so it's going to start to move, and force of friction is going to remain at its maximum value. Or actually, it gets slightly smaller. Why does it get slightly smaller? Because you're going from a static situation into a kinetic situation. Static from not moving, kinetic into moving. And when you switch from static to kinetic, you have to use a slightly different mu. And the kinetic mu's are smaller than the static ones. So once you start something moving, friction actually gets less, and it takes less force to resist the motion once it is moving. Okay? So mu stands for the coefficient of friction, and it's unitless. And we'll put some coefficients of friction on screen now.
Okay, so let's look at the different coefficients of friction and see what we see. I have a table here of materials and their static coefficient of friction and their kinetic, coefficient of friction. Notice that for each one, the static is bigger than the kinetic. 0.74 versus 0.57. Static is bigger. 0.61 versus 0.47. Static is bigger. We have the two surfaces over here, and notice it's always two surfaces. Steel on steel, aluminum on steel, copper on steel, and you can find different surfaces and get their coefficients of friction when those two different surfaces rub together. There's a certain coefficient of friction, and it is bigger for static than for kinetic. What we find is objects that have a low amount of friction don't slip very much. Things like ice on ice, you get a very small number, 0.1. And for things where you get much more friction, like steel on steel, it's a lot bigger, 0.74. Now, 0.74 is still a relatively small number, but it's a whole lot bigger than 0.1. And so you'll find that it's rare to get numbers over the number 1 here, although it does occasionally happen with certain materials. If you want to see your own table of coefficients of friction, you can just do a simple Google search. That's how I got this. I actually didn't use Google. I used Ocean Hero because it saves our oceans. But we can just do table of coefficients. It comes right up there, coefficients of friction. And you'll see that there are plenty of tables you can look at. And they're oh so pretty. So rubber on dry concrete, 1, that's a nice thing for driving. And you get the idea. Okay. Let's do this. Now that you kind of get an idea of what some of these are, let's go ahead and see if you can do some matching. Pause the video right here and match the force with the definition. Go ahead. Well, hopefully you got them right. Let's see what they are. The force of tension is a force pulling through a string on an object. The force normal is the perpendicular push of a surface on an object. The force of friction is the resistance of an object to slide parallel to the surface. And the force of gravity is the pull of the whole Earth on the object. All right.
One neat aspect of this formula is you can apply it to some neat situations you see around your life, as most of physics can be. But I'm thinking in particular of football linemen. If you've ever played football and been a lineman, they'll tell you lower man wins. They want you to get down in a three-point stance. That way when you start moving forward, you're also moving up. The idea is that if you push up on your opponent, so here is your opponent. That's not a pretty diagram. So that's your opponent. If you are pushing up on them, so that the force on them from you is going upward like that, so backward and upward, that's going to take away some of their force normal. Once you're lifting up on them, the turf beneath them doesn't need to push up as much. So it reduces their force normal. And if you reduce their force normal, you're also going to reduce their friction. And if they have less friction with the ground, they're going to be easier to move backward. That's why the football coach says, hey, don't push straight back, push up and back. Because once you reduce that force normal, you reduce their friction, they're easier to move back. Physics is everywhere. Now that we know our forces, we're going to put them in things called free body diagrams. These are pictures that show us visually the direction the force is going and what type of force it is. We have labeled arrows drawn outward in the direction of the force. And this is real important. You don't draw free body diagrams with the arrows pointing in. You always have them pointing out. You need to start somewhere where you're touching. Let's go to an example. The first example I want to do is a box in free fall. So think to yourself, of those 4 forces we talked about, gravity, normal, tension, and friction, which ones might be acting on this box? There could be 1, there could be 4. You can actually have multiple. You could have 6 tensions on if you had 6 strings attached. But in this case, there's nothing attached. The box is just falling through the air. You can imagine my tub. I'm using this a lot today. Imagine it's just falling. While it's in free fall, what force is acting on it? Well, the force of gravity. And so typically you have a dot in the center. The AP exam will often put a little circle to the side of it. Either way, you're going to have some dot I want you to put in the center or circle off to the side, and you will put an arrow going down. It's important that your arrows start within that given parameter and not off to the side of it. But we have one force going down. Notice the arrow is going out of the object, not into it. And we have to have a label. That arrow means nothing until we label it as force of gravity. So the only force acting on a box in free fall is force of gravity. I hope you thought of that. There's no force normal because there's no surface touching it. There's no force tension because there's no cable applied. And there's no friction because there's no surface it's sliding against. Let's try some other examples. Gotta get this board back. Ah, crikey. There we go. And that should be a screen there. How about a box that rests on a table? So here we have a box that rests on the table. What forces will be acting on it? Well, the table is pushing upward on it, and so there'll be a force going upward. What would we call that force perpendicular to the table? That is force normal. And gravity is still pulling down. Even though it's at rest on the table, gravity is still pulling it downward, and so coming downward is the pull of the earth, or force of gravity. One thing you want to do is make the relative lengths of these equivalent to their relative strength. So if we knew one force was much bigger than the other, then that arrow should be much longer than the other. In this case, if it's at rest, you would expect the forces to be about the same or the same length. And so the same length because they're the same magnitude. If you have 10 newtons going down, you should have 10 newtons going up. Or you'd ask yourself, why is it staying there? Because you'd have unbalanced forces. So if it's at rest, you can assume the forces are balanced or equal, not in the opposite direction. So you would have arrows about the same length. I want you to think about this one. What do you think we should draw for the free body diagram arrows? You can pause it, draw some yourself. Okay. Hopefully we got this. Coming downward, we have force of gravity. Going upward, we have force normal from the table. Going to the right, we have force normal from my hand. Now some people might call that the force of the hand. If you didn't want to call that the force normal from that finger of the hand, you could call that force, and you just write in the word hand, force of the hand. And it doesn't say whether there's friction on the table or not, but most tables do have friction. So we can assume there's probably some force friction in that direction. Okay? Notice that all the arrows came back to the same point. They were all drawn out, and they were all labeled. Okay? Lastly, we have this box pushed into a wall. So the box pushed into a wall, what forces are acting on that box? Again, we have force of the hand. And coming down will be the force of gravity. What would force normal on it? Well, our surface is up and down. Perpendicular to that would be out this way. So coming out of the wall would be the force normal from the wall. So which way does this thing want to move? It wants to slide down that way, parallel to the wall, and that means friction must act opposite that to oppose that motion, or upward. So force friction will be acting upward. And that would look like this. You know, I'm pushing something into a wall, only it's sort of a side view, imagine the wall's over there. So. Those are free body diagrams. They're very important when you do a problem in physics to first draw a free body diagram.